Okay, here's another problem from section 9.5. This is number 44. This is a significant one. This covers like a lot of the things we need to know for this section, so please make sure you really master this problem because this is really going to help. So here's our series, the n times x to the n over 4 to the n squared plus 1. Summation n equals 0 to infinity. So first we're going to use the ratio test to check for absolute convergence. So this is the limit as n approaches infinity of a sub n plus 1 over a sub n, the absolute value of that. And then we take the absolute value to check for absolute convergence. Remember, if it converges absolutely, then it converges. So we gets two birds with one stone. So we'll take the limit of this. So every time I see an n, I put an n plus 1. So this is n plus 1. Absolute value of x to the n plus 1. So I'm only going to use the absolute value on the x parts because the n's are always positive. All over 4 to the n plus 1. And every time I see an n, I put an n plus 1. So n plus 1 squared plus 1. And then just the reciprocal because I'm going to divide. So this is the reciprocal of that. So I've got this over here. 4n times n squared plus 1 all over n times the absolute value of x to the n. Okay. And then I can break this up into the absolute value of x to the n times the absolute value of x. Same thing with the 4 to the n, 4. And then I actually multiply this out. This is n squared plus 2n plus 1 plus another 1. Okay, and this stays the same. This is the same. Okay, then I multiply these. I put these next to each other. This is n plus 1, n squared plus 1. And then over here I just multiply this out. So that's n cubed, 2n squared, and then that's 2n. 1 plus 1 is 2 times n is 2n. So I put all my n's together, and the absolute value of x to the x over 4. Absolute value of x over 4. That's all that's left there. And then I actually multiply these out so it'll be easier to see. So this is going to be n cubed, all right, n squared, n, and 1. And this is still this n cubed, 2n squared, 2n. And this is my absolute value of x over 4. And again, if we look at the highest degree terms, they're both third degree, so that we look at the ratio of their coefficients, which is 1 over 1, which is 1. So this goes to 1, so this just equals the absolute value of x over 4, which equals L. Now this converges absolutely, which means it also converges when L is less than 1. So the absolute value of x over 4 is less than 1. That implies that the absolute value of x is less than 4. That's my radius of convergence, and x is between -4 and 4. So this is my interval of absolute convergence so far. I have to check the endpoints. And it's also an interval, possible interval of convergence, but I do have to check the endpoints. All right, so let's see what's happening at the endpoints here. I think we can see all that. There we go. Okay. All right. So first of all, check at -4. So I'll put -4 back in my original series. So where I saw an x, I put the -4. And I'm not taking the absolute value, just the series. And then I can take out the -1 and separate it. So this is n, -1 to the n, times 4 to the n over 4 to the n, n squared plus 1. So the 4 to the n's cancel, or they become 1, same idea. So I end up with this. And I put the -1 in front to the n over n times this. Now this is an alternating series. My my positive term without the alternating part is n over n squared plus 1. And for n greater than 1, and it just has to be some n. For n greater than 1, greater than or equal to 1, it's positive. It's decreasing. The series is decreasing. And the limit approaches, as n approaches infinity, is 0. So therefore, it converges by the alternating series test. So now at -4, it's part of the interval of convergence. So if you look down here on my answer over here, that's why I've got a bracket here at -4, because that does converge. Okay. Now let's check and see what happens at 4. If I put 4 into my series, I don't have the alternating series, so I can't use that test. And the 4 to the n's cancel, so I've got n over n squared plus 1. And if I just cross that out and I reduce that to 1 over n, that's a good comparison, so I'm going to compare that. So I'll use the limit comparison theorem. So I'll take the limit of my series, or the ratio, I should say the limit of the ratio of my series to the one I'm comparing it with 1 over n. I take the limit of that, so I would invert and multiply, so I get n squared over n squared plus 1. If I take the limit as n approaches infinity of that, I get 1. So since 1 is in this interval 0 to infinity, that means that both the series I started with and my comparison series, 1 over n, they both either diverge or converge. They both behave the same. So if one converges, the other one converges. If one diverges, the other one diverges, and that's by the limit comparison theorem. Well, since I know 1 over n diverges, and why, that would be by the p series. It's a harmonic series, but I should say p series. N equals 1. I should say, pardon me, p equals 1. Excuse me, p equals 1. And that since p is 1, it's got to be greater than 1 for it to converge, so it's equal to 1. So p equals 1, p series. So this diverges by the p series test. That means that my series also diverges by the limit comparison test. So therefore, it doesn't converge at 4, so that's why 4 is not in my interval of convergence. Negative 4 is, because it converges by the alternating series test. 4 isn't. Now let me check for absolute convergence at negative 4, because that might be here. It might be in my absolute convergence. Well, you can see it's not, but let's go show why it isn't. So I check negative 4. I take the absolute value of my series. Now this was the series I started with, but I simplified it, so this was an equivalent series, so I'm using this. And if I take the absolute value of that, it would eventually get this, n over n squared plus 1. But what does that look like? That looks like the series I just showed diverged by the limit comparison test. So this diverges by the limit comparison test also. Okay? So therefore, it does not converge at negative 4. Absolutely, I should say. It does not absolutely converge at negative 4. It converges, but not absolutely. Okay? All right, so we showed that it converged by the alternating series test, but it did not converge absolutely. All right? So therefore, it's on this interval of convergence, but it's not on the interval of absolute convergence, because it doesn't converge absolutely. So what happens if it converges but not absolutely? That's what we call conditional convergence. So at x equals negative 4, we have conditional convergence. It converges, but not absolutely. Okay, so if you understand all these concepts, that's about it. You're in good shape. You should be able to handle any of the other problems. So make sure you understand this and then apply this to all those other problems. And you have to spend a little time on this. Okay, so I hope that helps.